Good afternoon, all, and welcome to our WMG Colloquium Talks. It is my pleasure today to introduce our speaker, Professor Hamid Assadi from Brunel University, London, UK. Professor Assadi is expert in solidification research at BCAST, Brunel University, London. He received his PhD in material science and metallurgy from the University of Cambridge in 1996 and was awarded a research fellowship from the Alexander von Humboldt Foundation in 2004. His work experience includes a professorship at Tarbert Modares University and several visiting appointments at Helmut Schmid University, RWTH Aachen, Max Planck Institute for Iron Research, and the German Aerospace Center, DLR. Hamid has over 30 years of experience in multiphysics modeling of dynamic systems, ranging from materials processing to vehicular traffic, using various techniques such as cellular automata, the phase field method, and the mean field theory. He is interested in understanding the underlying mechanisms of dynamic materials phenomena, such as disorder and solute trapping during rapid solidification of alloys and intermetallics, besides physics-informed machine learning and software development. Today, he is going to present a talk on cold spray research, an overview with a few personal anecdotes. Thank you, Hamid, for your time, and stage is yours.
Thank you very much, Prakash, for inviting me. And it's a pleasure to share my experience of working on cold spray for now 25 years. So I'm going to also point out that this is the work of not only myself, but a large group of contributors, especially those with whom I worked at Helmut Schmid University in Germany. So I'm not going through the entire list of contributors, but you see the names. So cold spraying, for some of you, might be already a familiar topic, but for those of you who don't know anything about cold spray, this is basically a powder deposition method. Like any other thermal spraying method that you use powder and then you accelerate the powder particles and deposit them on a substrate to build coatings. And that's used for nowadays also additive manufacturing. The main difference between conventional thermal processing or thermal spraying processes is that the particles of the powder remain in the solid state. So it's basically the solid state deposition process. Why? Because if you manage to increase the processing temperature, you avoid oxidation and you avoid undesirable phase transformation. So that's the main motivation behind development of cold spray. Interestingly, you can use cold spray to deposit refractory materials, including tantalum, with a very high melting point, which you would have trouble with if you wanted to use conventional thermal spraying methods. So based on that, a main persistent question in cold spray research has always been, how does it work? So what's the mechanism behind that? I would say still maybe an open question. I would try to shed light on that a bit through the exposure to cold spray research. But I'm not going to give you probably the best answer to this question that we know so far. So that's the answer. The cold spray mechanism is based on what you see here. I'm not going through all the details, but I can assure you that's one of the best and more balanced answers I've ever seen. The only problem is that it's been generated by AI, not me. I think I would not be able to provide an equally good answer. You might say, well, this is maybe just a fancy way of Google search or plagiarism, high advanced plagiarism. But I think it actually brings to mind, if this is so advanced that could mimic human beings' answers, so what is left for me to do as a researcher? So if you think that this is not a big threat, then I would tell you that it is probably just the tip of the iceberg. Just a few days ago, maybe you've heard that NVIDIA is investing $100 billion in OpenAI, and that's not even a major partner of OpenAI, so probably have a lot more money. I'll give you an estimate of what $100 billion means. Is the money that you can run the entire UK universities for 1 year and left with some money to run other universities, other places in Europe. So it's a huge amount of money. So it is really maybe a bit different from all other technological advancements that we have seen in the past. Maybe it isn't, but it definitely needs some repositioning of researchers, or as Dimitri just mentioned, maybe rebranding of ourselves. So this talk, while I walk you through cold spray research that I was exposed to, is also meant as an advice about what lessons that we can learn from particular research activity, in this case cold spray, in order to reposition ourselves in the research community. So I would say, well, this is going to help humans, but I think equally might help AI developers, because they can see from the perspective of researchers, so what are the pitfalls, what are the limitations of AI at the moment? So maybe they can learn and then try to elevate AI to the level that it would be really difficult to beat. So this is going to be also for AI. Now, starting with a bit of cold spray history, a Russian scientist, not in manufacturing business, but studying the interaction between shock waves and metallic particles, presumably for aerospace research, where you have impact of tiny particles at supersonic velocities onto different substrates. He realized that when the two-phase particle and air were interacting with blunt objects, sometimes it would give him a hard time to scrape off the particles from the blunt objects. So it was like contamination of the blunt object by the particles that would be difficult to get rid of. So he sat on this for a while before realizing, this could be an idea for cold spray of substrates. So maybe as a thermal spraying process. So then he filed a patent, and that was the beginning of cold spray. So from this, I would say the main lesson to be learned is that, of course, you should avoid failure. So you shouldn't actually go for failure. But if failure does happen, then you should embrace it in the way that Popyrin did. So there is some value in not throwing away anything that you think is useless or rubbish. Another part of the history relates to a meeting between Heinrich Kreyer, a German physicist with an engineering mind in the United States. So he attends a presentation by Popyrin and then realizes, there is some interesting similarities between what he was interested in at the time, which was explosive cladding or explosive welding, and cold spray. So he took interest and he was intrigued by that, and then invited Popyrin to his lab. And Popyrin started to actually develop a cold spray nozzle you see here number C. So this is what Popurian made in Cryo's lab. And then Cryo took it and brought it to a level that is now being commercialized, and companies actually making things based on the design that was put together in Hamburg University. So the lesson here for me was that it is more important sometimes in research to be interested in what other people are doing rather than to try to impress people by what you know. So I would say in that sense, AI needs a lot to do because it always impresses us, but I don't know if it is impressed by anyone, although it actually gives you a lot of compliments sometimes when you ask anything. And this is a bit more personal. So during my time in Cambridge between 93 and 96, I was working with Frank Gertner. So he was a postdoc, I was a PhD student. And after that, during a reunion in 1999, Frank was giving a presentation about cold spray development in Helmstedt, and nobody had heard anything about it, I don't think at the time, or very few people. And then because I was a solidification researcher, he thought that it might be useful to have me over there for a short stay, research stay, to look at cold spray from solidification perspective, which later on became clear that was not really helpful in the sense that cold spray has, as we will see later, very little to do with solidification or melting. So the lesson here, never miss a reunion. By that, I mean the human touch, the connection between friends. That's beyond research and academia. So we just talk to friends and they talk about something at work, and then you take interest, and that becomes the beginning of a really fruitful collaboration. So when I went to Helmstedt University, at the time was called Universität der Bundeswehr, the University of the Federal Armed Forces in Hamburg. So Professor Cryo asked me, can you tell us anything about this characteristic velocity, which is called critical velocity of bonding? And that actually is the characteristic velocity that sets the boundary between no deposition, abrasion, and deposition from material science perspective or solidification. So that was the main question. What is this critical velocity related to? And I think it still is. So my approach was to study explosive welding, which was probably the main motivation from Cryo's side to get interested in cold spraying. See what is relevant here. What are the relevant microstructural phenomena? So we realized that in explosive welding, also you have a lot going on at the interface between two bonded bodies. Especially Cryo had done some work on the estimation of the strain, interfacial strain, using very interesting microscopy techniques. And he realized that there was like a strain of 10 at the interface happening during explosive welding. So that brought us to the question, so what is really similar? What are the similarities between cold spray and explosive welding, and how are they different? So that was the main task, to formulate the main questions in cold spray research. Now we looked at the what is called the parameter selection map for explosive welding. We realized that it's a fairly complex map. So it has 4 boundaries. The 2 boundaries at the side relate to speed of sound in the material and what is called the speed of the collision point. So based on the relationship between these 2 speeds, you can estimate the quality of bonding, or you can tell whether or not you will get bonding. But there was another boundary, and that was the more interesting one for me, and that was the boundary between what is called high velocity hydrodynamic deformation regime. So that's what's happening in explosive welding, actually manifested by a jet of material flowing out of the interface, and normal low velocity regime, which is like conventional classic deformation. So the transition between the two is something that we thought that might be also relevant for cold spray. But in cold spray, we have a problem because the angle between the substrate and the flowing object is not constant, because normally you have sphere. So a very subtle complexity coming from the geometrical considerations. So that was the difference. So with these in mind, then we started the research. So the next lesson would be that you, in research, probably in future, especially with AI, you should focus more on formulating questions rather than finding answers, because answers are nowadays available. And then, as a material scientist, the first thing I did, I looked at the correlation between this particular material property, critical velocity bonding, and other material properties. So you would think that melting temperature is probably the most relevant here, which is fairly true. So I plotted this critical velocity as a function of melting temperature. Here there is some correlation. But also you might think that because we're talking about kinetic energy, so probably density should also play a role. So we did that, and you can, if you push it too hard, you can say, well, there is a correlation. But I would say this doesn't tell much, because correlations can be misleading. So this is from a serious article, just stressing the same point, suggesting that, of course, light-heartedly, that if you eat more chocolate, you're more likely to win the Nobel Prize based on this correlation. Of course, there are some outliers. So you see that Germany probably needs to be easy on chocolate consumption. I don't know what's happening with Sweden here. But anyway, you see that as you eat more chocolate, then you have more Nobel Prize winners. So what do we learn is that correlation is not exactly causation. So that's a problem that you might come across in many different fields of research. And I don't know how well AI is currently doing in identifying that glitch. So I didn't give up on this correlation study. So I tried to come up with a kind of combined material property and plot critical velocity as a function of that. So this is the combined material property. So this is obtained from an energy balance, assuming that if you hit the particle on a rigid surface and then you resolve it in melting, so how would the kinetic energy correlate with the thermal properties? And I ended up with this. So you see that you will need half of the velocity, or a quarter of the kinetic energy that you will require for complete melting in order to have bonding. Still, it doesn't tell you anything about the mechanism, because it could or could not involve melting, because it's a highly localized deformation process. But what it does tell you is that thermophysical properties are relevant. So if you have particles at a higher temperatures, that probably they would bond better because of this correlation. So based on that, you can perceive cold spray as an extension of the thermal string process towards the lower thermal energy regime. And you can actually build up a plot like this that tells you where you should expect deposition based on the kinetic energy and the thermal energy. But the main problem is, so what about the mechanical properties? So if your particles are harder, what happens then? Because the experience was that harder particles have more bigger problem in order to stick to the substrate. So that actually drove me into using finite elements. So we used finite element simulation in order to study the interface of two impinging bodies. So looking at the interface, we realized that some regions of the interface, you have localized deformation during a very short period of time. What was a breakthrough then was looking at the single impact experiments, so single particle impact experiments, what they call wide tests. You could see that at the rim of the craters, there were some signs of bonding because there were residues of the impacting particles on the substrate. And later on, that was shown for other materials, here for titanium, that apparently the bonding does occur from the rim and then it propagates towards the south pole of the particle. So apparently there was some message here that based on this mechanical analysis, you could say this localized deformation has some role in bonding. And later on, we realized that this localized deformation is a very well-known phenomenon, but not in bonding, rather in fracture. So for materials that have this kind of capability to show localized deformation, normally this leads into instability in the formation and you lead to rupture. But in this case, we thought that it could be one of the factors playing a role in bonding. And this is called, in general, is called shear instability. But as I said, shear instability normally is something that you get during tension and it leads to rupture. But everything that we said is telling you where you should expect or how you should expect bonding, but it doesn't tell you anything about the mechanism of bonding. So on the mechanism, the common notion so far is that because metallic particles form a thin layer of oxide on the surface, and that will not allow perfect bonding. So the main role of interfacial deformation is to get rid of those oxides, either by ejecting them from the interface or making some spaces between the oxides by rupturing them. So that's probably the main mechanism for metals, but for other materials, I think it's still under development, and we don't know exactly how it works for instance, ceramics. So the lesson here was to differentiate between what is called a mechanism and what is regarded as criterion. So this shear instability should probably be regarded as like a criterion more than mechanism. Now, proceeding with the finite element simulation, we could then investigate the effect of various other parameters like the size of the particle. So doing some finite element simulation with heat transfer, so we realized that the larger particles are more prone to bonding, so you can get them bonded to the substrate at a lower velocity, impact velocity, because the time of the extraction of the heat with respect to the size of the particles become more prominent. So it's a bit of mathematical complexity here, but I think this has to do with the heat transfer equation and with the wave propagation equation, so that the way that they're formulated will give you that. The interesting point about this was that it could be actually verified by performing some large particle impact tests, whether or not particles anymore. They were bullets. So because of having the facility at the University of Federal Armed Forces, actually people could use real guns in order to shoot big bullets of copper on any substrate and see how they behave. So this trend was also experimentally verified at a large range of particle size. Now, if you take out the heat transfer, you will see that it doesn't really matter how large your particle is. And that's a bit counterintuitive because you think the larger particles carry a lot of kinetic energy at the same velocity, so they should provide a lot of energy for bonding, but apparently it's not the case. So this is one example of an analysis of using finite element for two cases where you have a 50 micron particle and where you have 50 millimeter particle at the same velocity impacting the substrate. And you see absolutely no difference if you have no heat transfer. There is another factor actually we took out, and that was strain rate sensitivity. So if you take that out, it doesn't matter if the particle is 50 micron or is 50 kilometers across. So what does it tell us? It's telling us that intuition is not knowledge. So if you think kinetic energy is responsible, or this is the main factor. Some analysis will show you that's not the case. Now, because, as I mentioned, mechanical properties are important. So the first thing that you need to know about the particle, apart from the thermophysical properties, is the mechanical property. But how can you extract something like UTS from a tiny micron-sized particle? So what we did also in Helmut-Schmidt University was to use a nan-indenter, but modify it. So instead of indenting anything, so we replaced the indenter with a flat head, and then we squeeze the particle, and then measure the load versus displacement in order to extract those constitutive properties. Now, why did we do that? Because there is an intrinsic difference between the microstructure of particles and bulk material, because they are produced in a different way. So the microstructure is forming at a very high cooling rate normally if you use atomization. So that's one thing. The other thing is that sometimes actually we don't even have the bulk data. So for M. Crowley, for instance, they are normally produced in the bulk, not in a bulk form, but in powder form. So because of that, then we need to come up with a way of measuring these mechanical properties. So if you look at the raw data of force displacement here, you see that for different particle sizes, you see quite a different kind of result. But it could be misleading because what you really need to look at here is not the raw data, but is kind of representative or characteristic stress versus strain. So by doing some simple mathematical transformation, actually you can plot some nominal stress value versus nominal strain, and you see that all the particles are also following almost the same trend. Now, the problem here is still how to extract the constitutive properties. Again, finite element can be helpful because for the particle under compression load, the elastic part can be handled analytically. Actually, the first person actually look at that problem from an analytical point of view was Hertz, the same Hertz, Irish Hertz, who is into electromagnetism. So when it gets to plastic regime, then it becomes extremely complex. So there is no analytical solution to the problem. So you need to use something like finite element or numerical simulation. So what you do, then you simulate that based on different input parameters, and then you make a comparison by adjusting those parameters that you feed in to your finite element analysis and the real experimental data, then you can work at the constitutive parameters. In this case, I think it's quite an interesting example where you use this technique in order to work out the constitutive parameters of bulk metallic glasses. That would be quite tricky if you want to do that during tensile testing because of the shear bands, the same phenomenon. They are unstable in plastic deformation and they break easily, so they show almost no ductility. But in compression is different. But still, you cannot get the flow stress versus flow strain easily because, as I said, it's unstable material under plastic deformation, unless you do something like this. So this is something that you wouldn't be able to see in any tensile testing, because as soon as you get the decrease of the flow stress with increase of strain, so you end up with strain softening, and that's a recipe for rupture. So use that for a lot of materials, including M-Crowley. So we could work at with good accuracy the value of constitutive parameters and also main mechanical properties like UTS and unit strength for also other materials. So the lesson here was to repurpose. So if you wanted to use nano-indentation, it would not give us the collective behavior of the particle under compression. It could actually give us something about local deformation. So you needed to look at this problem in a different way and use nano-indenter in a different way. So it was not nano-indentation anymore. The repurposing is something that probably AI needs to work on. Now, with the practical application, so you do a lot of experiments on the different conditions of the strain, and you end up that with a lot of correlations and with a lot of parameters. So this is a concise list of correlations and the parameters and factors that are relevant. Okay, so if you want to find the sweet spot by performing experiments with all these factors as a variable, you will not succeed because for each variable, so you need to increment that variable into within a range and then end up with performing like millions of experiments. So that's not feasible. So that's also a practical problem. So how to deal with this? Some people might be quick in saying that, oh, we can use machine learning. Good luck with that too, because first of all, we don't have enough data to train your machine learning stuff with it. And the second, who is going to use that? So are you going to make a software tool to give it to someone to who has expertise in Python and run it every time? So how is that going to work? So we thought about looking at this from a bit more physical point of view. So we plotted deposition efficiency, which is like how much you get deposited out of how much particle, versus various parameters, including the particle size, including the particle velocity. So you have a multi-dimensional space, and then you end up with a lot of scattered data points on any diagrams that you look at. However, if you simply divide this particle velocity by the critical velocity, you end up with a dimensionless parameter we call eta. And you realize that most of these scattered data points collapse onto one line or one curve. So that was quite interesting, because then instead of dealing with too many different variables, you could separate the effect of material properties from the process parameters and then bring everything into one single parameter, which is called eta. So I think eta is now being used for research, but probably not. But I think it's a very good rule of thumb in order to see where you're at in the code space. So basically, what happens is that you have some process parameters and some material parameters, and these have effects on impact conditions, also on critical conditions, which is critical velocity. So you can squeeze all of these into this eta, and based on that, then you can kind of estimate or predict the outcome of the cold spray deposition, not only for different process parameters, but also for different particle sizes and even for different materials. So that works, for instance, here in this particular case for titanium and copper. With the same eta value, you end up with the same normalized strength. Now, if I wanted to squeeze the entire cold spray research that I was involved with into one slide, that would be it. So eta should be taken as a measure of sprayability. So before, we thought that critical velocity is the measure. So we want to decide whether tantalum is easier to spray or magnesium. We look at the critical velocity, we see that for tantalum is less than, magnesium is more than 600 meters per second. So we say, oh, magnesium is more difficult, but that's not the case. So when you say which one is easier, you should not only look at the material, but also you should look at the setting or the process settings or the equipment. So if I want to give you a more tangible example, is like that. You can't judge a person saying that, oh, this is an easygoing person. But then I would say, in what context? It might be actually a very easygoing person as a friend, but maybe not as a colleague or other way around. So the same thing can be said about materials. So when you ask tantalum, the question about tantalum and magnesium, which one is easier, I would ask you first, what is your equipment? And what is your process gas pressure? And what is your temperature? And then I can tell you which one is easier. So here you see that, for instance, if you change the processing condition, then the difference between magnesium and tantalum in terms of sprayability becomes more profound. So that can be used directly into some sort of a software tool that you can use to estimate the sprayability, or even directly the properties of the cold spray deposits based on the primary processing factors. And this is one available software tool that actually gives you the value of theta for different, for, in this case, titanium powder. And you see that if theta is, eta is less than 1, then we end up with a porous titanium deposit. Whereas if you increase that into values above 1, then you get rid of much of those porosities. So this is the benefit of using that eta idea. So instead of just doing more and more experiments with different conditions, trying to consolidate all of these data into something that is more tangible and is easier to use. So that would be something that I think AI needs to learn in order to consolidate, not only try to generate more and more data through experiments. So the next and the final part is about my recent work here at Brunel around something which you can regard as a process between and explosive cladding, because in terms of the variation in geometry or impact angle, I think it's closer to cold spray, but in terms of is very close to explosive welding. So basically, here, instead of using explosive, use electromagnetic acceleration. This is something called EMPT that we have at Brunel. So we look at this together with colleagues led by Zardauli, who's now in Stellium. So we realize that if you look at the bonded region, you see that within the bonded region, not only the amount of plastic strain is high, but also the value of the plastic strain on either counterpart is almost the same. And that's what is normally regarded to as conformal deformation. So to needing a high amount of deformation, you need conformal deformation. That's an additional criteria for bonding, at least as far as EMPT is concerned. But back to cold spray, very recently, colleagues in the United States came up with a very interesting and thorough investigation of the strength, localized strength of the bonded interface for a micron-sized particle. So it's amazing work because it uses very advanced high-resolution microscopy in addition to very much controlled impact studies that you can use by this laser acceleration method. So here, the outcome was that not only you get bonding or no bonding in different regions of the interface, but also you can very accurately work at the value of the bond strength in different regions. And you see that in the South Pole, as expected, you see very weak bonding, whereas if you get closer to the rim, you have higher strength bonding. But everything said so far was about bonding between similar materials. So what if they are dissimilar? So the substrate has a different property. Then my friend Frank Gerdner came up with this idea, being a material physicist, expert in thermodynamics. He said, well, let's look at the enthalpy of mixing. And I said, what enthalpy of mixing has to do with cold spray? So there is no time for any chemical reaction, but apparently it does play a role. So if you take different combinations of different pairs of materials, particles and substrates, you see that for those materials that you have a positive enthalpy of mixing, so mixing is more difficult, then bonding is more difficult to achieve. So apparently there is some effect from chemistry, which hasn't been explored yet. And Frank and I always talk about a project that looking into this, which I hope that will happen in the future. So the final lesson is that sometimes you need to defocus and then refocus. So if you just look at the same tools that are available at your disposal and try to use them over and over again, so you will never be able to look at other possibilities. In this case, like what would be the role of the chemical composition, etc. So that refocusing is something that probably AI is not doing. So based on that, I would finish by the summary of these lessons. As a researcher, I think in order to reposition ourselves and try to compete with AI, first we need to accept it, we need to embrace it, we need to make the best use of it. At the same time, we need to position ourselves, I think that's my own experience, at least in cold spray, in order to justify our worth as a researcher. Thanks very much.
Mosde asking question. Eta is a dimensionless parameter, but is conceptually related to speed and does not depend on particle size or material properties. So how can it serve as a criteria for bonding? Also, is the critical velocity a well-defined parameter? I guess you said it is challenging to determine accurately.
Yes, thank you. I can see the question here. So no, eta is, if you remember, is a ratio, it's just a normalized impact velocity. But what you normalize it with is the critical velocity. And the critical velocity does depend on the material properties. Actually, mostly depends on material properties. So eta encapsulates everything, not only the process parameters, but also material properties. So conceptually related to speed and does not depend on particle size of material is not correct. So it does depend on properties. So when we introduced ETA, I think it was published in 2011 in Journal of Thermal Spray Technology. It actually also won a prize for that. I don't know whether you deserve it, but the concept was new. So if you want to dig into this more, so probably you can refer to that article in 2011. So the second part of the question related to the critical velocity is not well defined. You're correct. Still, yeah, I think it's a question of many other factors that is not considered in these idealized kind of simulations that we do, in idealized experiments that we use. So you're correct. So if you for instance talk about interlocking as a mechanism for bonding, for instance, then is it part of critical velocity or not? Or if you take a different material, so dissimilar materials, so what is the role of different material properties then? As far as I know, it hasn't been explored very well. So you're correct. It's not that well established, but it's the best that we have so far.
Thank you. Any other questions? You mentioned that electromagnetic pulse welding, right? Is it like industrially a good option compared to what automotive industries use, like resistance spot welding, something like that? Can it be possible?
I'm not quite aware of that. Maybe Zaidao could help in the future because they are into automotive manufacturing. But as far as I know, it's a very well established process now, especially in Germany. People manufacturing a lot of stuff. I don't know exactly where in the car manufacturing, but I can imagine easily that some parts, at least in the automotive and many other things that we might not be even aware of, will be using that technology. So yeah, it's a very well established technology. Yes.
So it comes under solid state welding technique.
It is solid state welding and doesn't have all the problems with the dealing with explosives, because not every lab will be happy to handle explosives.
Good. Thank you. Any further questions? Yeah, Jachi.
Hi, can you hear me?
Yeah.
Hi. Thanks, Professor Hamid. Thanks for your talk. So, I have one question. So, for the spread coating, do you need to consider the surface condition of your particles and your substrate, for example, oxidation and roughness? I'm asking because previously I had experience with accumulative row bonding. So using the row cold deformation to bond the sheets together. And in my case, the oxidation condition and the surface roughness is very important. I'm wondering, so if there's any learning from your research to a slightly different field, like accumulative row bonding. Thank you.
Yes, well, it's a very, very good point. I know that people have been looking at that specific question, and yes, it does play a role. But I think they focus on the level of oxidation on the particles rather than the substrates. For substrates, when we first wanted to introduce cold spray in different conferences, going around and say, well, why cold spray is good? I just mentioned two things. One was the fact that it is at solid state, so it reduces oxidation. The other one is that it inhibits phase transformation, etc. But that was another thing. So you don't really need surface preparation because it's kind of doing the job itself. So because you have like a beam of particle hitting the substrate, some particles around this beam are hitting the substrate at a lower velocity, so they do not actually stick to the substrate. They actually get out the um, um, the oxide layer. So they actually clean the substrate and say, well, this is why you need cold spray, because then you don't need to do much surface preparation. It does it in situ, which may not be absolutely correct. But sometimes we realize that in copper deposits, especially, the amount of oxygen inside the cold spray deposits were less than the oxygen of the feedstock powder.
Okay.
So not only the oxygen level would not go up, but it would also reduce. But still, going back to your question, yes. Why? Because I think when you have a thicker oxide layer, then breaking the oxide layer and exposing the fresh metallic surface would be more challenging. But I cannot say, I cannot tell, anything about the numbers, how much oxidation. But I think that's relevant. I wouldn't see that as a major problem.
Okay.
For spray, and I wouldn't see that also in your case. But I think Zaidao did some work, maybe EMPT regarding that question. Maybe he has some more information. But yes.
Okay, thank you very much. Thank you.
Thank you. Any further questions? If no more questions, oh yeah, Sampath.
Hi, Prakash. How are you? First of all, very interesting talk, Hamid. It was very interesting. Just a very quick introduction. So I lead the additive subtractive team at National Manufacturing Institute, Scotland. We are associated with University of Strathclyde, and we in 2023 got the Impact Innovation high pressure cold spray equipment. And since 2023, we have been working on cold spray, and one of the practical applications of that cold spray has been defined by the physical system itself of being capable of depositing multi-material in situ mixing of material for coating, let's say tribology application or corrosion resistance application. Now, obviously, we are still in the very early phases of understanding the process, and this talk has actually highlighted some of the points that we are thinking. How do you think the practicality of material mixing on the substrate can be understood based on the likes of, you mentioned the eta as a parameter where critical velocities are very important. Now we are talking about, let's say, mixing nickel with cobalt, chromium, and then depositing. How difficult will it be to establish that relation in terms of, especially, when OEMs look at this and we, from more practical point of view, try to solve that problem?
Well, the short answer to your question is that's very difficult, because after 25 years of cold spray research, I can still see a lot of problems with the application of ETA itself for a single particle or powder. So when you get to the blend, then I think not only does the problem get more complex, but also, I mean, there is another problem normally in technology in industry, that something needs to be really, really well established. So you need to have a lot of other considerations in mind, like standards, etc. So you can't actually go to the industry and say, well, this is the equipment, this is the software, you need to optimize your process, etc., and then say, well, that's fine. So anyway, it's not only about whether or not we can come up with an even more complex theoretical work to predict the behavior during cold spray deposition for powder blends. So that's one part. The other part is, what is it that you're going to do with it? So after 25 years, still we get, some comments and some ideas about, principles of cold spraying, very fundamental questions, how does it work, etc. And just leave metals and go to the ceramics. So what is the mechanism there? So you talk about blends, but what if one constituent is not metal but a ceramic? So it gets really more complex, and I don't think that we have addressed that question well enough. My recommendation or my thought would be that is a very good question. So I would see that as like maybe proposal for research or something. I would say, well, that's the way to go. But I'm not aware of any activities in that. So that trying to refine the theory or adapt it to powder blends. But yeah, but it would constitute a very, very good question, research question.
No, I agree. Thank you very much for your talk, and Prakash, thanks for the invitation.
Thank you, Srirangam. Thank you. Any further questions? If no more questions, as Professor Assadi suggested, let's start eating more chocolates. So one day we may end up with a Nobel Prize. With that lighter note, I thank you, Professor Assadi, for this nice talk.